And about the University of Alberta, we're a very large university. We're one of the largest in the top 5 in Canada. Where you see engineering here in this portion of the campus, and this is where I'm currently sitting. We have about $500 million average annual income in terms of our research in the university, and we got about 41,000 students. We've got about 18 faculties on 5 campuses, almost 400 undergraduate programs, and 500 graduate programs. So let's get on with the topic of today. I know I'm speaking to the converted, but let's go through a little bit some of the areas, not all, but some of the areas where thermophysical properties are important. Here I'm really focusing on surface tension, density, and viscosity. Of course, there's lots of others that need to be addressed and are important, but the technique we're going to talk about today addresses these 3. So whenever you're doing brazing, soldering, or welding, of course, this is a key point when you're trying to put, for example, solder balls onto a chip. Or when you're trying to cast a strip casting, particularly that meniscus formation is an absolutely critical part of the whole strip casting process. And being able to predict it and control it requires knowledge of viscosity, density, and surface tension. Lots of spray processes, both in extractive metallurgy. This is sort of an Outokumpu flash smelter. This is a spray deposition system, and this is a gas atomizing system. And all of these require very good knowledge of these 3 properties if we're able to control them and know how to operate these processes for different materials. And of course, not to go without, every talk these days includes a reference to additive manufacturing. In a way, it's kind of a welding type process, but to make these really small features, one really needs to understand these thermophysical properties of these metals and alloys. Of all the methods that are used for making these measurements, and I'm going to just focus as an example here on surface tension, there are really fundamental conditions that are really met in order to make those measurements. One is the potential force induced by gravity, and here density, of course, is a relevant property. And at the same time, we're looking at these potential forces as they act opposite surface tension forces. And there we're looking at either the shape of the liquid or the shape of a bubble that is pushed into a liquid bath. And essentially, the balance between these 2 is given often by the bond number, which is the potential force relative to the surface tension force. And basically, then you measure some experimental variable that enables you to calculate the surface tension. And all these methods involve and require us to know what the density of the material is. And so that one example of surface tension leads us to say that we need more than one technique to be able to measure all these 3 properties. Here I'm going to talk about 2 different examples. One is the sessile drop technique that everybody's read about and knows about and maybe even practices. Here we put a droplet onto a substrate and essentially over time measure the curvature, take pictures and then model the curvature of this droplet as a function of time, and then basically try to calculate the surface tension from that function. But you notice that density is one of the parameters. When you do the maximum bubble pressure technique, you basically pressurize a gas, form a bubble, and then watch and see what pressure that bubble is released and the bubble is released from a known height of immersion. And that surface tension, again, is measured from this maximum pressure calculation. But again, the density is here and needs to be known to be able to do this measurement. All of these techniques, these two included, there are certainties in terms of what the shape of that bubble is, unless you use X-rays to look through the metal, to look at it to see whether it is wetting the orifice coming out of the tube or not, and here whether it is wetting the the shape of the droplet onto the substrate. Of course, the droplet starts off as a particle that has an oxide coating on it, and one has to remove that oxide coating. So there are lots of complications. Typically, these are one measurement per experimental condition. So you go through a bunch of bubbles coming out, and you get basically an average surface tension. And here, one droplet will lead to one measurement condition. Wetting is an issue. Well, we'll talk about wetting with regard to discharge crucible towards the end. And they don't reflect really dynamic conditions in that the fluid is largely stationary. And then if you want the viscosity, you have to do a separate experiment to do it. And as I've said, density must be predetermined. There is one technique that allows you to do all three values, all three measurements in one experiment. And that is the electromagnetic levitation system, where you have basically two induction coils. That one is basically to heat the sample, and one is to levitate a 6 millimeter droplet that you see here. You have a high-speed camera, a pyrometer, and a cooling gas that's running over the sample. You can do a lot of gases. It's non-contact. It's containerless. So it really keeps the sample nice and clean. On the Earth, you can do these measurements by getting the surface tension and the density. But in order to get the viscosity, you've got to go into space. You've got to go into microgravity conditions. And there is an EML system on these International Space Station. So you can imagine if you want to do all three measurements of a single sample, it's a very expensive process, and both in terms of cost and time. So let's look at the discharge crucible method and what the principles of the technique really are. Imagine you've got a crucible or a container of some dimension, and you put a small orifice or a small hole in the bottom of that crucible, and you allow the fluid to flow. To be able to follow the flow or to predict the flow of that fluid, we're familiar with the Bernoulli equation, where we balance things against the pressure difference on both sides, the change in height, the change in the velocity at the interface here and at the exit of the orifice, and that equals any change in velocity with respect to time. If you choose the right set of conditions, this term here ends up being relatively constant. There isn't really a change in velocity with time. If you do this in atmospheric conditions, both on top and below, this term will also disappear. And so you're basically left with these two terms, usually, under non-inviscid conditions. So you basically can get the, with no viscous losses, get the velocity as a function of position. Usually this orifice is very small compared to this one. And this is basically, this equation comes from a differential balance on a differential element of a stream just about to exit the orifice. Important assumption in this derivation is that the stream diameter coming out here is exactly the same as the orifice diameter. So we are not assuming any wetting taking place between the fluid exiting and the orifice of the bottom of the crucible. Okay, so way back when, back in the year 2000 or so, when we started doing this work, we were actually doing some consulting work for Alcoa, trying to do some granulation, and we were having trouble getting the flow rate from the flow from the crucible, because we need to know what the flow rate is to know what the right frequency is to form monodispersed sized granules. And we weren't getting agreement at all with our measured flow rates and our predicted flow rates. So we decided to do a few little quick experiments using water here at different temperatures and ethylene, using the Bernoulli equation, and basically trying to see what the discharge, what the friction losses were. Now, ordinarily, all of these curves should fit on one curve because we're looking at using the same type of system, same geometry, same orifice. There was no wetting taking place, and so the friction losses should be the same. But as you see here, we didn't get agreement between these different experiments. So we decided to look at the different forces that were at play. And here's the potential force that you can see that was acting for a good part of the portion of all the forces. Here you see the kinetic force. This is the inertial force of the fluid exiting. But then here's the surface force that we see below here. And we see it particularly at the low heads. The surface force was quite significant. So we realized that we were missing a term in the Bernoulli equation. And so just for interest's sake, I'm not going to go through all the details, but we basically went ahead and incorporated the term of the surface energy into the Bernoulli equation. And here you see the accounting for friction losses, which is a function of flow rate, density, and viscosity. And so you get this equation that says that the flow rate of the fluid exiting the orifice is a function of the friction losses, the size of the orifice, the height, the surface tension, and the density. And when we basically took the data from the previous experiment and replotted it, incorporating this equation, we basically got all the discharge crucible, all the discharge coefficients falling onto the same curve. So we knew that we had accounted for this was the missing term that we had dealt with, that we were missing before. But it dawned on us also that we can take this equation and turn it around and solve, for example, for surface tension, density, and viscosity here, because of the fact that as you're draining the crucible, if you measure the change in height with time, and if you measure the flow rate exiting the orifice as a function of time, then you have, in a simple experiment, even if you've got 100 milliliters of a fluid in the crucible, you've got over 100 data points. And so these three parameters of viscosity, surface tension, and density are three unknowns for a material with unknown properties, and you've got 100 data points to try to fit and find the best values of these three properties that are agreeing with the flow conditions that are in the obtained in the experiment. If you put this equation in dimensionless form, what you get here is the Froude number plus 1 over the Bond number is equal to 1. So again, we're getting potential forces, we're getting inertial forces, and we're getting the gravity forces at play here. So it follows the fundamentals of what we expect to see for a method that's trying to measure these properties. Actually, I'm going to digress a little bit. So then we did try to do measurements on aluminum and magnesium alloys, which I'll show you a bit later. But that was a bit Foolish of us, but whenever you start something new, you're always doing something foolish. And then the student that was working on this successfully got his master's, moved on. Years went by, and then Professor Moser one day came visiting me in my office and said, "Would you like to try this on tin?" And I said, "I'd love to. I wish I could find the funds and the opportunity to be able to push this method a bit further and try it on lower melting point metals so that we can really test it, because aluminum is very reactive, as everybody really knows." And so from there, and by the way, the reason Professor Moser was in Edmonton is because his daughter lived around the corner from my house. So small world. So make a long story short, after a couple of visits to Poland and to the Institute, I met Tomac at those days, and then Tomac came over and did some experiments in our lab, and then also did some experiments back in Krakow, and these are some of his results. So basically what you do is you do an experiment where you collect weight as a function of time, and this is for tin, and this is the size of the orifice that was done and the temperature. Of course, this was done in an argon atmosphere, and this is done with different temperatures to make sure that we can get a good calibration of the discharge coefficient as a function of Reynolds number. And on there, we were also checking it with water at 2 different temperatures. And from there, we plot the surface tension as a function of temperature, as I've indicated to you before. And these are the brown circles are the results of Tomac's work, compared with other people's results that were done using different techniques. And over on the right, you can see now with tin silver alloys. Again, this is Tomac's work, where he compares it with other published work using other techniques, and the agreement is quite good. This is for surface tension. For viscosity, I'm showing here the tin silver for different compositions. The work we've done was the work that Tomac again did with the DC method are the diamonds, red diamonds that are here, and then the other method are using a modified capillary for viscosity measurements. You can see here we've got the 34.6 tin silver. Here's the 3.8 curve, and this is the pure tin curve. And so the 34.6 curve sort of saddles between 55 silver and 32 silver measured by the modified capillary method. So we're getting good agreement with classical methods. And of course, these classical methods have to measure, again, each of these properties separately. While this data came, viscosity came along with the surface tension and the density. Here is some more of Tomac's work showing the measurement of antimony. His work is shown here, the stars, the red stars, in very good agreement with other work that was done using other techniques. Here's on the right, a tin antimony alloy. Again, showing here the black points are the different alloy compositions, agreeing quite well with the other alloy compositions and measurements that were done. And this is just showing the surface tension that were done using other techniques that are published in the literature. So this we're showing here, in this case, surface tension, but at the same time, we also got viscosity and density. The one thing I'm not going to talk about is how this data fits with theoretical models of these properties, but that's another topic, maybe for another talk. I wanted to kind of focus on the experiment and the methodology of getting data and how it compares with other measurements. So this is the viscosity for the tin antimony, shown here in the black data points, compared with those measured again by other workers, showing very good agreement with other workers' results using other techniques. So we're pretty happy and pretty confident. This is now the original, some of the original work that was done in the early days by Stephen Roach. Here is number 3 is our data for the surface tension of aluminum, and this is under oxygen saturated conditions. Here is the 2% variation, and this analysis was done by Professor Mills, Ken Mills. Unfortunately, he has passed away, but he had done this thorough review of the surface tension properties of pure metals. It's an excellent publication. I recommend you to dig it out and have a good read of it. But he found that our technique was quite accurate in terms of getting the properties of the material. So we're bolstered and felt more confidence with the technique from after reading his analysis of our work. Here's the surface tension of AZ91D. It's a very common magnesium alloy. And we did this measurement. It was a difficult set of experiments that were done under argon and SF6. SF6 is a very common gas used for protecting magnesium during commercial processing. It's being replaced because it's environmentally poor. It's a really horrible gas for climate change and for CO2 impact on the atmosphere. But here's the surface tension as a function of temperature, and this is with argon up at the top here, and we see that the presence of SF6 reduces that surface tension of the magnesium alloy. And it does so by basically forming a protective layer on its surface. And that's one of the mechanisms that lead to its reduction in its surface tension. So that tells us the technique is able to not just get the properties, but get the properties as a function of the atmosphere that the material is in. However, I mentioned before that one has to be careful about wetting. So this is more recent work done by Pat Flood, who has just finished his master's thesis about a year ago. And so here we're looking at aluminum, results of aluminum, and looking at the volumetric flow rate of aluminum as a function of Reynolds number. Now, these are experimental results, the blue line shown here. But if you look in the literature and use the literature values for surface tension, viscosity, and density, this is the flow rate that one should be getting. And the reason for the difference between the two is that these experiments were done using alumina crucibles. And liquid aluminum metal very nicely wets alumina ceramic. And so we're seeing a reduction in the flow rate as a result of the wetting. Here on the right, we see the same results. This is the experimental, the experimental measurement is below here in blue. The predicted measurement is in green, and this is for an aluminum copper alloy. Again, with an experiment done using alumina as a crucible. All the previous work that was done on aluminum was done using graphite. And so here we see that the choice of material you use and if it results in wetting can dramatically affect the results that you get. And it will affect the parameters that you get at the end in terms of density, but it turned out that the viscosity and the surface tension were still quite acceptable. Here we see the evidence of what we believe to be the evidence for the wetting of the orifice. These are 3 experiments of aluminum in the alumina crucibles. Here we're looking at flow rate from the literature using literature values for the properties divided by the measured value of the flow rate as a function of time. And you can see in all these 3 temperature cases, we are less than 1 as a ratio, indicating that we are observing a flow rate that is slower than should be the case if we did not have wetting at the crucible, at the orifice exit. On the right here, we see the capillary number. And the capillary number looks at our viscous forces relative to our surface tension forces. And if we have no wetting, this should be constant. But as you can see, we're plotting time here of the experiment. We're starting over here and ending up over here. So we're starting with a high capillary number, ending up with a much lower capillary number. And the capillary number is changing as the experiment is carried on. And so that's a clear indication of wetting. Okay, so that's, and the wetting basically results in the fact that the density does not agree with, one doesn't get good values for density, but the surface tension and the viscosity still provides good work. So where are we now? So when we saw that, we said, well, we need to upgrade the way we're doing the experiment. And so we built this new device where we have basically, sorry, I'm competing with this laser pointer that's going through here. So we basically have two sections here. One is the furnace section where we have an induction furnace. The crucible sits in it. We'll have we have a thermocouple inside, and we're going to have a laser looking from the top down into the melt. And this laser will give us a direct measure of the height of the liquid in the crucible as it flows out. Because up to this point, we've been getting the height by calibrating the crucible ahead of time and back calculating after we get the weight of material that goes on the load cell, we back calculate where the height was in the crucible. But this time we're going to be having a laser giving us a direct measure of the height of the liquid in the crucible. And then we also collect the load cell that gives us the weight of material as a function of time, as a function of time that is landing on the crucible. This will be an improvement because by having the height, when you start with this experiment with a known weight of material in your crucible, once it's molten and it's at a known temperature, with the laser, you measure its height, bang, right there, we know the density at that temperature. And so therefore, becomes an input into the model. And then the load cell information afterwards gets used to be able to calculate the surface tension and the viscosity. So again, we're still using the same device and getting 3 properties. One additional improvement, we're putting in here a oxygen getter where we put some titanium chips over a heater to be able to control and reduce the oxygen content to a prescribed known level. So this unit is shown here on the left. This is the top is removed with the induction coil and the water cooling and the induction cables power coming in. Here you see the spot where the laser unit would be sitting. And this is a pyrometer that's sitting over to the right, a viewing port, and then an extra port in case one is needed. And then the load cell sits near the bottom. The whole thing sits at about a meter and a half in height and about 0.2 meters in diameter. So it's a lot easier to control the atmosphere than the unit that Tomac was using many years ago. So we're in the process of commissioning this unit. One of the current things that we're also looking at is to look more closely at the orifice and at the orifice geometry. The orifice geometry plays an important role in the function of this technique. And so we've been looking at breaking down the parameters of designing the orifice, that is the chamfer that's here, the height of that chamfer, the width of that chamfer, the angle of that chamfer, as well as the diameter. And you can see here we can express the viscous losses as a function of those parameters. And we can basically control those parameters through machining to be within certain ranges. We put in a set of parameters. We've been doing experiments with water, for example, and we can see here that we're looking at experiments versus a model that uses those parameters. We see at the top left here 3 different designs of orifices, sim angle, but different depths, and the length of the orifice here is different. This is a measured discharge crucible, measured discharge coefficient as a function of Reynolds number for the 3 different geometries, and you can see there are some small differences in the friction factor, in the discharge coefficient, which you would expect because the geometry is different. And those differences, even though they appear small here, they could affect the prediction of properties to some degree. And so we've put in the parameters of these orifices into the model, as I showed in the previous slide, and compared the prediction of the discharge coefficient as a function of these measured values, which you see here. And this is for water. And we got really good agreement between those cases. And so we're currently looking at what is the optimum design of orifice that one should have in order to, as you'll see in a minute, maximize the effective forces that are taking place as the crucible is emptying. So here's a case where we're doing, this is a model case, looking at 2 different cases where we're designing in the model a crucible of this geometry versus another crucible of this geometry running with aluminum alloy at a melting point. And here you see when we run the model for those 2 crucible designs, here's the total. This is the balance of forces, or the energy distribution for crucible 1 and the energy distribution for crucible 2. This is the total that we see, the red line in both cases. The Froude number starts off being quite high and ends up being low. The bond number starts off low and ends up high. And the viscous losses are relatively small with this kind of a design. On the other hand, with this other design here, you see the Froude number starts off much lower. The bond number is higher than it was in Crucible 1 and ends up to be, starts off actually quite high, but ends up 40% of the energy is still in the surface tension or the surface forces, the bond number. And here you see the viscous forces, they start off low, but they go up and they're almost 50% or a little over 40%. So by changing the orifice design, one can improve the sensitivity of the method towards being able to get, the right balance of forces and the right values of more accurate values of surface tension, density, and viscosity. So currently, we're looking at developing a model for looking at accounting for wetting. Hopefully, we can get a contact angle in addition to what we've been getting so far. And we're looking at optimizing the orifice design. So what our future work, as I said, we're looking at optimizing nozzle design and optimum data analysis to reduce error. we still need to determine the minimize the uncertainty of the parameters. We need to, by choosing the optimal design of orifice, we're basically optimizing or minimizing the error in getting the different three property values: density, viscosity, and surface tension. We're also extending the model to account for wetting phenomena to get dynamic contact angle in addition, and we're planning high temperature experiments to look at aluminum alloys, and steels. Of course, we're going to start with tin and some low melting point materials. So with that, I'd like to acknowledge our funders. NSERC is our national funding agency, pardon me. ESA, because we're collaborating with our thermoprop colleagues in DLR and in other places in Europe to do experiments on the EML, comparing it with the measurements with the DC unit. Equispheres is a company in Canada that does atomization, and DLR is our partners in thermoprop for doing the experiments on the ISS with the EML that we will be comparing with the DC method. I want to also acknowledge Jean-Sébastien Roll at IGL Nancy. Our current student, Quentin Champ-d'Oiseau, is doing a joint PhD between us and Université de Lorraine in France. I want to acknowledge Tomac, who's been really a champion of pushing and getting a lot of data published on the DC method. He's been doing fantastically well. I think he's now a full prof in Krakow. I'm looking forward to hearing more about how he's progressed. And of course, our group members, Steve Roach was the originator and the co-inventor of this technique. Aziz Bonio was a research associate and started off as a postdoc and research associate. He's since left since last March and joined industry. Quentin is currently a PhD student. Pat Flood is a master's student that finished about a year ago. So with that, that's the presentation, and I'm happy to take any questions.
You know that there are some technologies as for casting that are related to semi-solid processing. So yes, you can go Reo casting, for instance. And yes, there is a colleague that I will send you this presentation from Brazil, which is Eugenio Zocchi, and that I don't see here, but he will have some troubles maybe in the communication, that he would like to extend. He's working basically in thixoforming, so in very high fraction of solids in the liquid, but is interested in Reo casting, so very low fraction of solids. So how about, the possible behavior, in, would say, a little bit of more high viscosity, like going up with the viscosity. When you have the semi-solid range, you can have some 10 times more, even 20 or more in Reo casting, depending, of course, on the solid fraction. Do you think it could be useful, or it could be a mess because there are particles that are sticking? There are
yes. Well,
it's just an idea.
Yeah, I know, and I can only respond in theory. Okay, I cannot say for sure, but I'm going to share again. I'm going to go back to the original equation that I showed, the Bernoulli equation, and I think in principle, one would be adding this term in the model, because the exerted pressure would be on this end would be higher than the exit pressure. And so one would, because you'd have to get the material to force it out of an orifice. So if you have no wetting, you can probably do that only. But if there is wetting at the orifice, then one would have to add some additional modeling terms, which we're currently working on. So it would be a more complicated setup because you'd have to pressurize the top and not the bottom, and it would be also a more complicated model. But I think in theory, it should be feasible to do?
Another question is that will you really explore steels, because steels,
Yes.
this area of our course is mainly related to steel properties, so I have sort of initiative for the whole 20 and 22 year, which is called Steel for Future. And actually it would be fantastic because steel processing is complicated. Of course, you have continuous casting. Of course, there is also the development of new steels, so-called lightweight steels, so very highly alloyed, especially with aluminum. So again, it's a trouble. And I think even knowing about the density, which is in the liquid state, would not be so easy. So they are much more alloyed than 1% of aluminum, and so you go into the full aluminum manganese, typically steels, and which is a topic which is very interesting because one needs to go to lightweighting of steels, and on the other hand, there are very big troubles in casting them because it's nearly impossible to go into continuous casting as far as you just go ingot casting, and so I think it is a really technological hot topic about it. And then, but if I would like to have some other guys making question, or Thomas saying more observation, because he is also a professional in the field, not like me. The other point is that the algorithms for solving your data that you are collecting are basically non-linear would say equations that you should solve numerically. Is there any progress, or you are still using the same algorithms that you were using in the past? Because this is fantastic. You can, please.
We've been improving the algorithm considerably. Because that's one of the areas where we're trying to increase or decrease the level of uncertainty, and to do that you've got to look at different algorithms to be able to improve the accuracy of predictions and the level of uncertainty. But I also wanted to go back to your comment about steel, and I'm going to go back and just show you this slide again. This unit that we built it with the intention of going up to 1700 degrees Celsius. So this induction coil is powered by a 20 kilowatt induction furnace. So our intent is to go that high in temperature and to be able to look at steels or super alloys for that matter. Now, since we have such a wonderful international audience here, let me be shameless and plug collaboration. NSERC, our funding agency in Canada, has started a new program called the Alliance International. And the Alliance International is one where it enables us in Canada to collaborate and get funding to collaborate in research with colleagues abroad. But the way it works is our colleagues abroad, when they write a proposal, if they would like to collaborate with us, they would include us in the proposal that they write in their home country or in Europe or continent, right?
For sure.
They would include us. And once your proposal is reviewed and approved, we need to submit within 3 months a proposal to NSERC asking for funds so that we can do the work in collaboration that's been promised in our collaborators' proposal. And by doing that, we're able to get some funds over a 3-year period to do the work in collaboration. And that means our graduate students can be able to fly back and forth. We can exchange materials, we can exchange data, and so on and so forth. So we're more than delighted to engage in these collaborations. We're allowed one of these proposals per year. And so, we're happy to collaborate and to extend this technique and to share it with other people.
For sure. As for me, I would be personally happy, but I think there will be also other possibilities because we are really from some different parts of the world. So I will spread the word, and possibly who is fit better than you will join. But as for me, I would be happy to do that because I'm really interested, especially, we were thinking about with those colleagues in Brazil, but also for myself and for my past work, which was for a period of my life on copper alloys. But now I think maybe aluminum would be very good. Maybe steel would be very good. So anything, and of course I am in a research institution, and I would be pleased to. So it's good that you have said it explicitly, and I'm also explicitly available for any possible process and of going on. But anyone in other parts of the world is also, I think Hani is very open-minded, and I think you have a lot of work to do, and to find even some other guys, some young guys to do, like Thomas has done in the past, to do some experimental work, which is always nice if you have the right devices and the new technique like it is this one. So I wish you more and more success with this technique, because I believe it is very, very competitive. I have been starting again to try to have some information about, I would say, viscosimeters, and they are so expensive, the industrial viscosimeters, that's your way is much better because it saves time and it is consistent. So when there is something which is not working, you can check it and think again, like you are doing. And I think it is the right way. Totally, it is the new thing.
You're right, Fabio, and maybe we should hear from Tomac, because Tomac went through the process of using different techniques to make measurements. And he used the same alloys on the discharge crucible. I know this go back many years. And he used the discharge crucible to make the same measurements. And so he can tell us the level of effort that it's taken him many years ago to do and collect all these three properties using different techniques versus getting it from the discharge crucible. Do you want to share with us, Tomac, your experience?
Yeah, sure. Yeah, I have a lot of time spent with the discharge crucible method. So maybe I back to the question of semi-solid, Fabio. I think the better technique for the measure viscosity is the rotation method. So rotation the crucible, or I think
yes, probably you have some of your colleagues have it in Krakow, because they have a very nice institute there. They're working very seriously. They are very serious guys, and so. But I don't have it, so I'm looking for this one. But I think the approach by Hani is fantastic, because I've been erratically working on the physical properties of liquid metals, and I think having all measuring at once, it's fantastic. And I wish you a very good success in the field, for instance, of steels, highly alloyed steels and so on, which for process parameters, for simulation, for casting simulation, there are inputs that you really need. I mean, something that... So pleased to be in contact with everyone, and pleased to meet you again. Thomas has been visiting me some summers ago, because we have some seaside, so we combine a visit both scientifically. We made a summer school, but he had also the possibility to go to our sea, and I hope we will be back meeting one another soon. And I think it's very nice to go on in your direction, Hani. Of course, maybe Thomas, for other reasons that I've told you, maybe I will visit you sooner than you believe, because I must pick up these guys, unfortunately, from Ukraine. And if they will reach you or they reach you Poland, I will pick them up by my car, because they need to be moved from this terribly situation to safer situations. So I don't want to speak too much. Please, Thomas, why don't you show yourself, and I will disappear from the screen, and then if you have the possibility to switch on, if you are without troubles, or otherwise it's okay in any case. But I'm happy that you have joined us, really, and I'm happy that Hani has also that possibility. So, Hani, will you have the possibility also to host some people, yes, for doing some experimental work? I think so. Or we can manage some days or what else in your own I think so.
People are more than welcome to come and visit us and share, and we can formulate collaborations. But I want to hear Tomac's comments first.
Me too. Yes.
Yeah, go ahead, Tomac.
Okay. When I compare, the methods, especially from the surface tension, there is the tricky was with the whole of the crucible. When I talk with the master student of the Hani, he have a lot problem with the obtained the good results from the aluminum. So I try to explain him how to start, to calibrate, etc., etc. But then when I realized he used the alumina crucible, then I realized, okay, you have the problem with the wetting. So so then I talk with I use the angle 45 degree. So in my opinion, this is when I prepare this crucible for many during this calibration and trying to get the best results without any wetting, especially when I use only the graphite crucible in my experience. So then I realized that I don't have the wetting. I don't have this problem as he has. So we are just talking about, and he had tried to check the different angles as the Hani show in this presentation. This is the problem was with the wetting by the aluminum crucible. But the Hani also showed the compared two methods. This is the Discharge crucible method and the capillary method. The capillary method, that was we have built some equipment for this experiment, and the viscosity, I think this is the best method for the viscosity. But the crucible was from the quartz. So and the problem was for the different materials, we can't use this crucible with this capillary, because we have the problem with the temperature and also with the materials which we study start doing some films on these crucibles, and we don't get the good result. But for the tin and silver, that was the very good equipment. I have a lot experiment with the alumina. I spent alumina magnesium alloys. We have the published, I think, a few years ago, this paper. But I spent maybe 2 years to calculate and get the properly value of the surface tension. That was the very challenge to try to fit together the three to get the three value of the density and viscosity and surface tension properly. Regarding to the possibility to doing some experiment with the Hani in Alberta, finally they built the tower. This is the finally the place of this tower, or you plan to move another time, Hani?
The tower that you used to use for your experiments, we now use exclusively for atomization. We built this new system, which we call our thermoprop unit. We've basically invested a lot of money into building this unit that will be just exclusively used for a discharge crucible.
Wow, perfect. So I think that this method is very potential from the steel. This is the high temperature. I don't in Krakow I built some equipment, but this is the equipment to 800, maybe that this is the maximum of the temperature when I can use this equipment. But from the steel, I think this is the very good method to measure the viscosity, surface tension, and density.
Yes, and if I may add, Annie and Thomas as well, I have some friends and some colleagues in France in this Jean Lemour Institute in Nancy, and also some friends and colleagues in the steel R&D department of a company which is based here in Italy, which are from ACM, which is in Metz, which is not so far from Nancy, and there are some 20 guys devoted to R&D on steels of an Italian company. So I think we should try to do something together, even in steels, because it's fantastic to have some this device, and I think especially for developing new steels which have properties that you cannot use the software if you don't have the physical properties. It's nonsense.
Exactly.
Which properties is it? Yeah, the properties of pure iron. Well, it's another story. So I think it's something to explore. And so if possible, I will try to lay down some proposals that can be then reproposed in your line, so that we can do and interact together, because there is so many things to learn and so many things in this specific field that I don't think it is some sort of competition, because there is all so many technical alloys, so many elements that you can do experiments. It's something, but it is a very new, exciting field in my mind. Okay.
Yep.
Yeah. So, any other observations from people from other parts of the world? I would be happy to have, if possible. I think, for instance, Luca Milani, I don't think he's now here, but he's from Vesuvius. Vesuvius is a company which is manufacturing, is from Vesuvius, Italy. I don't know. I've seen that maybe he's not here. And so there are some other guys from chiefly from R&D. Nicoletta Bruno is from R&D company of Danieli, which is a very important company in steel making plant. And so there are some other guys as well. But as for me, I'm perfectly interested in developing new things. And if you're already at a good new starting point, it's fantastic. Okay? So we will keep in contact by email, Hani, or all of you. And you, Thomas, maybe I will visit you quite soon. If these guys, they try to find their way from Ukraine to anywhere else, I will reach them in Poland or in Hungary or in Romania or what else, because I want try really to have them for a period, which is important as well.
We are also in the Krakow. We have some program also from the research people from the Ukraine. My head of the director, she go to take from the border this guy, the Yuri Plevachuk. He currently is in the Bratislava with the family, but he back to the Lvov. He will be defended the city, so he decide to defend.
Mamma mia, we say in Italian. It's something that it is unbelievable to be in such a situation. Of course, full support, and we of course we all hope that they will stop combating. And it's nonsense. I've been spending just 1 month, but where there was Gorbachev for my thesis many years ago, and so it was in Moscow. But and then I was flying from Ukraine that was Kiev to Moscow. It's crazy. This is very crazy situation. Hope it will stop, because for our Europe it is something dangerous and very worrying, and for the people involved it's really a risk of their life. So
totally,
So, Hani, happy to see you in a way again.
Yes, and this is
the useful part of the pandemics, that we can use these remote talks without troubles. Before we didn't, but now we have started, and we will have. I will be pleased if you have any possible further meeting, I would be, because we will keep all the year long activities. So if you have some connection, then you can promote your own approach, university and devices. I'm really pleased to do it. Okay.
Thank you.
Thank you. Really,
keep me on your list. I'd love to hear other people's talks and other people's work.
Yeah,
I'd love to hear what people are doing.
Yeah, okay. I will inform you.
Participate in future as an audience member in future seminars. This is great.
Yeah, thank you so much, and thank you to all of you, Thomas. My special regards and best regards to all of you around the world.